the recording on the computer. Thanks everyone who were on Zoom and mentioned that there were a small technical glitch. All right, so we had been looking into applications of diodes, and one of the major applications that we looked at was basically clipper circuit. We also looked at half wave and full wave rectifiers, which is one of the very important applications for a PN junction diode. And then in the last lecture, we also looked at clipper circuits. We just started looking into clamping circuit. That is the last thing that we're going to discuss about diodes. And then we'll move on to BJTs and MOSFETs. So you have seen how diodes work. It's basically a p-type semiconductor and an n-type semiconductor placed very close to each other, because of which they create this depletion region. And you know what happens when you have forward bias or reverse bias, both from equations and from intuitive understanding. Let me see if I can go to a later slide. Yep. So we did the half-wave rectification, and we saw clipper circuits and different examples of clipper circuit. One thing to keep in mind when you are trying to solve any problem with clipper circuit, always try to see when the diode is going to be forward biased or reverse biased. Of course, if the diode is forward biased, for an ideal diode, it's a short. So the voltage across the diode becomes zero for an ideal diode. For a real diode, of course, the voltage drop across the diode is 0.7 volt when it is forward biased, because the diode itself has a drop of 0.7 volt, which is the threshold voltage of the diode. If the diode is reverse biased, it's an open. So the entire voltage drop happens across the diode. Just keep that in mind, and all the analysis will become very simple. So, for example, we looked into multiple different scenarios of clipper circuit in the last lecture. So this was a series clipper, and series clipper means that the diode comes in the series path, the diode itself in the series path, and then there is a shunt path which goes to ground or which goes to the negative terminal. And you are looking at the voltage across that shunt resistor, which means that when you have the positive half cycle of the sine wave, and in all these cases, we are assuming that the input is a sine wave. You can always assume other inputs too, but the sine wave is always the easiest or the easier one to understand. So that's why for all discussions related to diodes, we are considering the input as a sine wave, and we are looking at the output as a function of the input. So of course, in this case, in the positive half cycle, the diode becomes reverse biased. So the entire voltage drop happens across the diode. The output resistor does not get anything. And that is why you see zero in the positive half cycle. In the negative half cycle, the diode is forward biased. And in that case, the entire voltage drop is happening across the resistor. However, if you bias the series clipper, and depending on the direction of the battery that you place, just analyze that, okay, what happens if my input is a little bit positive or input is a little bit negative? So if this battery is of 1 volt, then what is happening when you have, for example, if you have a positive, let's say 1 volt. If you are at positive 1 volt, you are applying 1 volt over here. In that case, because this 1 volt battery is connected in the opposite polarity to your input. So you have positive over here, the battery positive is here, and you have the battery negative here. So the input 1 volt and this 1 volt of the battery kind of cancels out. So the diode is still in the reverse bias region. And if the diode is still in the reverse bias region, you still get the output. So that's why if you draw a 1 volt line over here, a horizontal line, whatever is below 1 volt, the diode is still reverse biased in that condition. And so whatever is below 1 volt, for that, you'll see the output. On the other hand, if the polarity of the battery is reversed, now you have the negative here and the positive here. In that case, let me clear this. In that case, you can analyze that, okay, if my input voltage is, let's say, minus 1 volt, if my input voltage is minus 1 volt, and the battery is connected in a way that you have the negative over here and the positive over here. So the minus 1 volt, even in the minus 1 volt condition, or right after the minus 1 volt condition, you start seeing that the diode becomes reverse biased. But if the input is higher than minus 1 volt, if the input is anything higher than minus 1 volt, the diode stays forward biased. And if the diode stays forward biased, the diode becomes a short. Okay. Or basically, yeah. So you can analyze whether the diode becomes a forward bias or a reverse bias depending on the scenarios that you see here. And depending on that, you can figure out what would be your final output. Okay? That's how Clipper circuits work. Now, we wanted to take a look at clamping circuit as well in today's lecture before we move on to BJTs and MOSFETs. So how clampers work is that you move the entire signal up and down. Clipper was removing part of the signal. So when you had the Clipper circuit, you are removing part of the signal. But with clampers, you are moving the entire signal up or down, depending on the way the signal is connected or your circuit or the diode has been connected. So let's take a look at this example where you are applying an input, which is, let's say, this kind of a square wave. You can also apply a sine wave. It doesn't matter that much. But let's say you are applying a square wave like this, which you see over here from V to minus V. So when you are in the positive half cycle here, when you have the positive half cycle, this part, because this is an AC signal, the capacitor, let's say it stays it offers very small amount of resistance to the AC signal, let's just say. Now, in the positive half cycle, the diode is forward biased. So this diode is forward biased. So the diode is conducting and it's a short. Now you have a resistance in parallel to a short. What would be the effective resistance in that case? 0. So whatever voltage you want to develop at the output, that will be 0 because the resistance overall is 0 for an ideal diode. So in the positive half cycle, you'll actually get a 0 voltage at the output. Now, what is happening at the negative half cycle? In the negative half cycle, the diode becomes reverse biased. So you have a voltage here and here in the negative half cycle. You have a positive voltage in the bottom terminal and a negative voltage in the top terminal, and the diode becomes reverse biased. Now, if you consider the reverse bias diode, of course, the voltage drop happens across the diode. The entire voltage drop is happening across the diode. But at the same time, you're also storing this voltage on the capacitor because the capacitor is an energy storage element. So in this condition, when you have the negative half cycle, you are storing the voltage on the capacitor. And in the next cycle, when you have the positive half cycle, again, what you'll see is that the diode becomes a short. So at the output, you have a short. However, in the next time when you have a negative half cycle, what happens in that condition is because the capacitor already stored this voltage, what would happen in the negative half cycle is that you're seeing a voltage that is applied here. Let's say that maximum voltage is Vm, Vmax. Also at the same time, the capacitor has the same stored voltage Vmax because that's the property of the capacitor. It will store the voltage or it will store the charge. So overall, what you have stored in the negative half cycle, in the next negative half cycle, is twice Vm. So one Vm is coming from the applied input voltage. The other Vm is basically coming in because you have a stored voltage on the capacitor. So you have twice the amount of voltage from the second cycle onward. The first cycle, you do not have that 2 times the voltage at the output. But the second cycle onward, you will have 0 voltage during the positive half cycle and minus 2 volt in the negative half cycle. And then that will repeat. So here you see that the entire square wave that you had at your input is kind of pushed down. And this is called a clamping circuit because what you are effectively doing that you're clamping the DC point. So for example, this was your DC biasing point initially, right? Or the common mode voltage. So you're clamping the common mode voltage to some other voltage value, which is over here, right? It's the same square wave. It's still the same square wave, which is going up and down like this, but around a different DC voltage or different common mode voltage because everything has been pushed down by 1 Vm. Now, just like you had biased clipper circuits, you can also have biased clamper circuits. So in this case, for example, as you see that the direction of the diode has been reversed. So in the positive half cycle, the diode will stay reverse biased. In the negative half cycle, the diode will become forward biased. So in the negative half cycle, you would have otherwise have 0 volts for the previous scenario. If I go back to the previous slide, you saw that in the half cycle where the diode is forward biased, your output voltage is 0, right? The same thing happens in this case as well. When the diode is forward biased, your output would have been 0 unless and until this battery were present. So because this battery is present in this case, and you'll see a minus 10 volt for the battery. So basically your DC is being shifted by this 20 volt biased with this 10 volt battery. So instead of 0 volt, you'll see minus 10 volt. So effectively what you can say that in this case, the entire voltage, which was from 0 to 20 volt, this kind of a sine wave, if this battery was not present, then this entire thing would have been pushed up by 20 volts. Because again, in the first cycle where, or the first half cycle, where the diode is reverse biased, you store the input voltage, the amount of input voltage or the maximum amount of input voltage in the capacitor. And then you use that stored capacitor voltage to clamp up the original input voltage at the output. So without the capacitor, the output would have looked something like this, a sine wave where the minimum voltage is 0 and the maximum would have been 40 volts. But because this is a 10 volt, and because of the way the polarity of the battery is drawn, or the polarity of the battery is connected, you'll not see a 20 volt clamp up. Instead, you'll just see a 10 volt clamp up, because the battery is connected in the negative direction and it adds a minus 10 volts. Yes. So it will go to plus 50 and plus 10. So flip the battery. So just imagine this, that when your input is 0 volts, how much would have been the output voltage? Right? You flip the battery, your input is 0, how much would be the output voltage? Because the diode is forward biased, the output voltage, when you flip the battery, the output voltage will be plus 10 volts, right? And this is a clamper circuit, which means that everything will be clamped up by how much amount? By this 20 volt amount. So this is what your input is. This is how it would have looked like without any kind of bias. This is what it looks like with the bias that you have connected now, a minus 10 volt. So that pushes it down by 10 volt. If you flip the battery polarity, it would look something like this. But the minimum point will be plus 10 volt, and this will be 50 volts. Right? Why is that? Again, think about it. When your input is 0, at that point, what would be the output? The output will be plus 10 volt if you flip the battery. And the output would be minus 10 volt in this condition, the way the battery is connected now. All right. Okay, so similarly, this is basically a summary page, which you can use as a reference for different kind of clamping networks. Again, something that is very easy to remember. Again, this may not be the case all the time, but the way this circuit is drawn, when this diode is pointing downwards, you're clamping the voltage down. And that's just because, yeah, we are defining the input voltage in a way that this is positive and this is negative. If you define the input voltage in the opposite way, even if the diode points downwards, it will not. So basically, just be careful about when the diode becomes forward bias and when it becomes reverse bias, depending on the way you are connecting the input. Okay. So in this case, if you define your input voltage in the manner that this is the positive side and this is the negative side, the diode is clamping down. So your input, which originally looked like this, will be clamped down to this on the right-hand side. Now, if you had a bias voltage like this, and again, this is the scenario when you have the positive polarity on the top side and the negative polarity on the bottom side. So when you do not have any input, even in that case, you basically have this plus 10 volts. Or this point gets mapped to the plus 10 volts. Similarly, if you flip the polarity, you'll go to minus 10 volt over here. And then this is 2 times the original amplitude of the voltage. You can flip the polarity of the diode as well. And in that case, you just start seeing the input voltage being clamped in the other direction. So now the input voltage is being clamped up. So your output looks like this. If you bias it with a positive voltage, this was your question earlier, that what would happen if you bias this with a positive voltage, then everything will be shifted by the amount of voltage that you have in the battery. And then if you bias it with a negative voltage, then it will be shifted down a little bit more. So all you need to think about is what is the polarity of the voltages and by how much you are shifting it up and down. All right. So you can actually keep on using this theory. The idea is that you store the voltage in a capacitor and then use the stored voltage in the capacitor in the next half cycle. So you can use the same concept to create voltage doublers, voltage triplets, voltage quadruplets, and so on. So how do you do that? So let's say you have this circuit, okay, and the output of this, you will see that we are going to calculate the output of this particular circuit, and we are going to do that in the next slide. Vm is the peak secondary voltage in the transformer. So Vm is the voltage that you have on the transformer. That's a peak voltage. And in the positive half cycle of that Vm, for the positive half cycle of this voltage, your D1 diode, this will conduct, right? And the capacitor gets charged to Vm. When this diode is conducting, the capacitor gets charged to Vm. Why? Because again, as the diode is conducting, the drop across the diode is 0. So of course, the voltage drop has to happen across the other component, which is the capacitor in this case. The same thing that we had seen earlier for the clamper circuit as well. That when the diode is forward biased, because the voltage drop across the diode is 0, the voltage has to drop across the other component, which is the capacitor in this case. And that capacitor voltage is equal to Vm. Now in the negative half cycle, the diode D1 will be switched off. So this diode will be switched off because this is positive and this is negative in the negative half cycle. The diode D2 will start conducting, and the capacitor C2 is going to charge to twice Vm. Why would it charge to twice Vm? Because this point is positive, this point is plus, and this point is minus for the Vm voltage. And this is minus and this is plus for the Vm voltage that are stored in the capacitor C1. So in the first half cycle, when you're storing the charge, it was stored in this direction, right? Because the voltage was, the entire voltage drop happened across the capacitor C1. So you know that the charge storage across the capacitor will look like this. So in the next half cycle, if you have this as plus, this as minus, this as plus, and this as minus, and you have Vm voltage here and another Vm voltage stored in capacitor C1. So that was the original voltage that you started with in the negative half cycle. So this capacitor C2 is going to see twice the amount of Vm voltage in the negative half cycle. So the capacitor C2 will charge to twice Vm, and the polarity will be, this is going to be plus and the top terminal is going to be minus. You can use the same concept to continue increasing the amount of voltage. So of course, you can use the voltage doubler, which was this part that you had seen earlier. You connect another diode and capacitor with it, you get a voltage tripler. You get another diode and capacitor with it, you get a voltage quadrupler, and so on. Okay. So, and then you can keep on adding more and more stages, ideally. But realistically, you cannot do that because the diode itself has a loss. So of course, if you are starting with just a 1 volt, right? Or maybe 1 volt or 2 volt, then you have a diode drop of 0.7 volt. So what you're going to double is basically the voltage that is left after having the diode drop. So having more and more diodes becomes not that interesting after a few stages. If you start with a very high voltage, then yeah, you can still continue doing it. But then the diode has to withstand that very high voltage and still have a very low threshold voltage, which does not happen in reality. So if you have only a few volts to start with, maybe you want to just double it or quadruple it, but you don't keep on making it 8x, 16x, 32x. That doesn't make much sense because you need those many diodes and you'll have those many diode drops in the circuit. Ideally, it's possible. All right. So there are a few more slides on Zener diodes and maybe a question, a mathematical formulation of Zener diodes. I'll not go through that, but rather we are going to start our discussions on BJTs. So please make sure that you go through the section on Zener diodes as a self-study. But now what we are going to look at for the remainder of the lecture is BJTs, and the next lecture I want to start with MOSFETs. Now for BJTs, there are two different types of constructions. And if you think about it in a very simplistic form, BJTs are nothing but two PN junction diodes connected back to back. So a PN junction diode was P followed by an N, or N followed by a P. For BJT, you are going to have P, N, and P, or N, P, and N. So you can have two different constructions, PNP type BJT or an NPN type BJT. Now, eventually what you have in that case is three terminals. So that diode was a two-terminal device. You had the P terminal and the N terminal, but the BJT creates a three-terminal device. And these three terminals are called emitters, base, and collector. The three terminals are going to be called emitter, base, and collector. The emitter will mean the emitter of majority carriers. So we already learned about majority carriers when we were discussing diodes. Emitter will be the emitter of the majority carriers in the type of transistor that you're using. So if you have a PNP, your emitter is a P-type semiconductor. And inside the P-type semiconductor, you know that the majority carriers are the holes. On the other hand, for NPN, the majority carriers will be electrons because you have an N-type emitter. So the majority carriers will be the majority carrier for N-type semiconductor, which are electrons. So in this case, for example, for the PNP scenario, if we just take it for granted that, okay, emitter is the emitter of holes and the collector is the collector of holes. So basically you are sending holes from the emitter side to the collector side. And you know the direction of flow for the holes will be same as the direction for current. On the other hand, the direction of flow of electron is opposite to the direction of current flow because electrons are negatively charged particles. Now, in this scenario, when you have the PNP transistor, how can you make the current flow from left to right? So from emitter to your collector. So for that, you need to have a positive voltage connected to your emitter terminal, right? And you need to have a negative voltage connected to your collector terminal. So these two voltages are going to be called, let's say, VEE and VCC. Right? So just like your supplies that you use, YCC because it's the collector terminal, and YE it's because it's the emitter terminal, the battery you have connected to the emitter terminal. And the base terminal is connected in between. We'll come to that what is the job of the base terminal. It basically controls the amount of current flow. For resistors or for resistors, you know that you can connect a voltage across a resistor, and then that creates a current flow if you are having a voltage connected between these two terminals. For diodes, you know that the current flows in only one direction, but not in the other direction. So you have some control on the current that flows through the diode device. However, you cannot control the amount of, for a particular amount of diode voltage. So let's say you have this diode, and then you have connected, let's say, some kind of a voltage across it. So if this voltage is fixed, you cannot control the current that flows through the diode. You can only control the direction of the current by flipping the polarity of the voltage, but you cannot control the amount of current that flows through the diode. But for a BJT, you have a third terminal which you use as a control terminal. For MOSFETs, you also have the same thing. That control terminal is called a gate terminal for a MOSFET. For BJT, that control terminal is called a base terminal. So transistors, in general, you'll see that in some books they call it 3-terminal, some books call it 4-terminal devices as well. We'll get to see why some books do call them 4-terminal devices, and in reality they are 4-terminal devices. We just don't use the 4th terminal, which is the bulk or the body of the semiconductor material, because any transistor is created inside a semiconductor. And if you have P, N, and P, creating your basically the BJT transistor within a semiconductor. So let's say you have a semiconductor wafer. So a semiconductor wafer basically looks like a round. I don't know if how many of you have seen a wafer, but maybe I can bring some in the class later on and show that it's basically a circular disc. And the circular disc could be, let's say, maybe 6-inch in diameter or 8-inch in diameter. However, this transistor is in micrometer. The size of the transistor is in micrometers. And in advanced technology nodes, you'll see MOSFETs, the size of the MOSFET will be in nanometer scale. So that's very, very small. So you can actually have billions and billions of transistors on this one circular or one disk of wafer. So if these transistors are placed here, here, and so on, so you know that the PNP, the P, N, and P, all those 3 terminals are somewhere over here. But you'll see that and it will be clear when you discuss MOSFETs from the next lecture onwards, that you may also need to bias the bulk or the body of the semiconductor. That this device is here, but until and unless you bias, let's say put a voltage here, and that voltage could be 0 volt or the supply voltage as well, depending on what kind of transistor you're using. So you also need to bias the entire semiconductor as well. And that is called the body terminal. That generally is termed as the 4th terminal. We'll not discuss the 4th terminal today, but when you discuss MOSFETs, I think that 4th terminal will be clearer. But for now, only 3 terminal is good enough. 1 terminal is the emitter or the source of the majority carriers. 1 terminal is the collector or sink of the majority carriers. And the 3rd terminal is the control terminal. All right. Now, how does this transistor operate? To make sure that the transistor operates correctly, the emitter to base junction is forward biased. So this is the PN junction diode. The emitter to base junction is forward biased. Of course, you will connect the P type of the positive side of the battery to the emitter and the negative side of the battery to the base, so that this PN junction is forward biased. The base collector junction is reverse biased. So the base collector junction, that needs to be reverse biased for correct operation of the PNP transistor, or for any transistor in that case. In this case, just that you're reverse biasing the base collector junction, which means that you're connecting the negative end of the battery to the collector and the positive end of the battery to the base. All right. So what does that do? So from the emitter, it's basically, so if you think about an NPN transistor now, the NPN is the source of majority carriers, which will be electrons. The emitter side is the source of majority carriers. And the collector side would be the collector of majority carriers. Now, if you're forward biasing the emitter to base junction and reverse biasing the base to collector junction, what would happen in this case? So this is just the opposite of the previous slide. The previous slide was a PNP transistor. So you saw that the polarity of the base to or the emitter to base voltage source, or the polarity of the base to collector voltage source, was just the opposite in the previous slide. If I go back, so you see that the polarities were in a way that you had the positive side of the battery to the P terminal of the transistor, and the negative side of the battery here to the other P terminal, which is the collector terminal. So you want to forward bias. You want to forward bias this side, and you want to reverse bias this side. And we'll see that why we want to do that. But for now, let's say you have this transistor, which is again an NPN transistor in this case. So it's just you still want to forward bias the emitter to base junction. So this is forward biasing the emitter to base junction, and you want to reverse bias the base to collector junction. So in that case, your current flow is from here through the transistor to the other side. Also, at the same time, you have some amount of current in the base terminal as well. Now, the total amount of emitter current is the sum of the collector current and the base current. So and that is because of Kirchhoff's law, that, okay, you have the amount of current that is getting emitted from this device will be the total amount of current that is being sent to the device. So the total emitter current is equal to collector current plus base current. And the collector current itself is comprised of two different currents. One you can call as the majority carrier, so the current that is being created by the majority carriers, and the amount of current that is being created by the minority carriers. Now, if you think about the input characteristic for the BJT, that input versus output, that depends on what kind of configuration you are using. And by configuration, what we mean is that there are three terminals. So this is basically the representation of a BJT. So this is an N, P, N. And similarly, there is the symbol for the PNP BJT looks like this. For the PNP BJT, the symbol looks like this. Now, the direction of the arrow, it is interesting to remember what would be the direction of the arrow for NPN or PNP type BJT. The arrow is always drawn on the emitter. Whether it's an NPN BJT or a PNP BJT, the arrow is always drawn on the emitter side, and the direction of the arrow points to the flow of the current on the emitter side. The direction of the arrow points toward the flow of the current on the emitter side. So for an NPN BJT, this is basically your emitter, this is your collector, and this is your base. So you will have some amount of current flow from this base to emitter junction, and you have some amount of current flow from the collector to emitter. And the total amount of those two current will be the current that will be flowing through the emitter terminal. On the other hand, for a PNP BJT, the current flows in through the emitter terminal, because again, for a PNP BJT, the majority carriers are the holes, right? Because the P-type semiconductor has majority carriers as holes. So the direction of current flow, the direction of flow of holes is same as the direction of flow of the current. So that's why for the emitter terminal, the current flows in this direction. And that current gets divided into two parts. A little bit of that current flows out here in the base, and most of that current flows to the collector terminal. Yes.
So why is that for PNP? Just like a little confused on the convention for that. Why is like the emitter not, I mean, it's technically like collecting current.
Okay, so the way the emitter and collector, the names are, this could be very confusing, and that's why the nomenclature is set in a way that the emitter is always the emitter of majority carriers. The emitter is not emitter of current. Okay. The emitter is not emitter of current, rather the emitter is the emitter of majority carrier. So whatever majority carrier you have, for an NPN, the majority carrier is electron. For the PNP, the majority carrier are the holes. And the direction of the current through the emitter, that is represented by that. So basically for an NPN, that's how the symbol of the NPN looks like. For a PNP, this is how the symbol of the PNP looks like. For PNP, the current comes in through the emitter. On the other hand, for the NPN, the current goes out of the emitter. All right. Now, eventually, we'll see that what is the purpose of the BJT, or why would you even want to have a BJT. But if you have a three-terminal device, you can basically use or have your input across two of those terminals and have your output across two of them, right? So there are three terminals. You can have one terminal as a common terminal. So for example, let's say you can connect have your base as your common terminal and connect your input between the emitter and base, and see your output across the collector and base. So your input could be across these two terminals, and your output could be the other two terminals. Or basically, keeping the base terminal as a common terminal, you can see the output across the collector. So this configuration will be called a common base configuration, that your input is between emitter and base, the output is in between base and collector, and basically the base is common between the two. And that's the reason why it is called a common base configuration. Now for a common base amplifier, and again, many of these things will be clearer when we go to MOSFETs and then come back to BJT again. And that's why I want to discuss MOSFETs first, starting the next lecture, because I understand that many of these things are not becoming clear today. The common base amplifier, the input characteristic looks like this. This looks very similar to a diode. And the input characteristic is defined as the current that flows in the emitter terminal. So because your input is the emitter, remember that, okay, if I go back to the previous slide again, your base was the common terminal, your emitter was the input, and your collector was the output. That's how we define the common base configuration. So emitter is the input terminal. So what would be the input voltage? The input voltage would be the emitter voltage with respect to the base, because the base was the reference of the common terminal. What is the emitter voltage with respect to the base? That's going to be, let's say, your VBE, or the base to emitter voltage. What is the input current? That is the current at the input terminal. And because the input terminal is the emitter, you are showing the IE, that's the emitter terminal's current, on the y-axis. Now, because the input kind of looks like a diode, right? It's either a PNP or an NPN BJT. So that means that the input side emitter to base could be either a P to N or an N to P. So it's still a diode. And the characteristic of that diode will be same as what you have seen before. So basically, this is the voltage IV characteristic, the input current to the input voltage. This is looking exactly like a diode, but depending on the collector to base voltage, there is another something that we haven't considered yet, is what is happening at the output side. So depending on the voltage that you set at the output, and that is the biasing voltage of the output, you will see that these curves could look very similar, but they will not superimpose on each other. Depending on what is the collector to base voltage, whether that is, let's say, 20 volts, 10 volts, or 1 volt, you will see different amounts of current, or this curve will be a little different with respect to VBE. And this is called the input characteristic. The output characteristic, on the other hand, looks like this. Again, we'll come back to all these things when we start discussing MOSFETs in the next lecture. Today is just for you to see how the input or output characteristic looks like. We're not going to prove them, or we're not going to talk about why they look like this for today's lecture. So similarly, the output characteristic is the output current plotted on the y-axis versus the output voltage plotted on the x-axis. The output current is, of course, on the collector terminal, because our output is at the collector. So IC, that's the collector terminal, is your y-axis. And the output voltage is the output side voltage with respect to the reference. The reference was your base. So VCB, the collector to base voltage, is your output side voltage here. And again, you'll see that for different amounts of input current, so I equal to 0, 1, 2, 3, 4, 5, 6, and so on, and different input currents are created by different input voltages. So you can also think of it as these curves being generated by different amount of VBE voltages, base to emitter voltages. Depending on that, you'll see all these different curves. Now you see that after a certain point, after a certain VCB, after a certain point on this right-hand side, the current at the output is not dependent on the voltage at the output. The voltage at the output keeps on changing in this direction, but the current remains constant. That is a property of a current source, right? So if you have a current source, if you want to design a current source, what do you want out of the current source? You just want current. You just want a fixed amount of current. Let's say 1 milliampere or 5 milliampere and so on. You don't want the current across the or current coming out of the current source to change depending on how much voltage is developed across the current source because of any circuit that you connect to it. That's our assumption, right? Whenever we see an ideal current source, we assume that the current is fixed. And this is the first time you're seeing that how that current source can actually be formed. We still didn't go into the theory, the physics yet. That we'll do from next lecture onward. But look at this region. Look at this entire region. The current at the output does not depend on the voltage at the output. It's a fixed quantity. It depends on something else. We'll come to that. But it's a fixed current source. And that is why BJTs or any kind of transistors, BJTs or MOSFETs, they are modeled as a current source. So in our first homework or during the first few lectures, I told that any kind of transistor will eventually be modeled as a current source. And this is the reason behind that, because the output characteristic of the op-amp becomes flat after a certain point. Of course, it's not a current source in this region. It's not a current source in this region. It's only a current source in this region. Yes.
Would be, I mean, actually, but one that's dependent and a different source with a be independent?
Great question. So the question is this a dependent current source or an independent current source? And the answer is here already in the slide. See that the value of the current source is not depending on the voltage at the output, but it's depending on something. It's depending on something else. It is depending on the current at the input side. So as you change the current at the input side, the current at the output changes. And that is the reason why BJTs will also be called a current-controlled current source. The control is coming from a current, and the output is also a current. On the other hand, MOSFETs, as you'll see when we discuss MOSFETs, are going to be voltage-controlled current sources. MOSFETs will have a voltage at its gate, and the output current will be a function of the voltage at the gate. And that's the basic difference between BJT and MOSFET. Everything else is very, very similar in terms of the operation. In terms of the physics, again, they are very different. But in terms of the operation in a circuit, they are very similar in that respect. Now, in this particular plot, you see that there are three regions. One is called a cutoff region, one is active region, and one is called the saturation region. Yes, question. Voltage controlled voltage sources. So you can use, like for example, the BJTs and MOSFETs that we'll be seeing in this course are not voltage sources. But in terms of device physics, also I am not sure that I can call anything as a voltage source, because at the end of the day, you'll see in any kind of device that you use, eventually you'll create a current. Of course, you can map that to a voltage by multiplying that with a resistance, right? But the eventual device physics will determine that it becomes a current. And so you can either have voltage controlled current sources or current controlled current sources. But I don't know of a, let's say, a voltage controlled voltage source in an ideal or in a real one.
The transformer would be like a self-transfer.
Yes. So eventually, I mean, why I said that is even for a transformer, it's a current that gets induced, right? It's electromagnetic field, and magnetic field creates a current in the primary to secondary. Capacitive coupling, you can call it a voltage because that's E-field coupling instead of magnetic field coupling. So capacitive coupling, you can say that eventually you create a voltage which is not dependent on the current. But that's also, it's not a device. It's basically a coupling mechanism between two different plates of capacitor. Okay? So if you talk about devices, I think everything that we are interested in electronic circuit are going to be a current source eventually. So there are three different regions here. One is called the cutoff region. And the cutoff region is where your input current is so small that you cannot even create an output current. however large your output voltage is, you do not create, or you create a very small amount of output current. So that is the cutoff region. This region over here, which will be called saturation region for a BJT, and we'll come back to that in the next lecture when you discuss MOSFETs as well. And we'll see that what is the physics behind these two regions, the region where the output current changes as a function of the output voltage, and the region where the output current does not change as a function of the output voltage. So there will be two different regions, and the application of these two regions will be very different. Yes. Is it possible to shift the regions? Yes, of course. So if your VCB is very small, then you are in the saturation region. If your collector, it is possible. But that deals with, for example, you cannot do that as a circuit designer. You have to do that as someone who designs the actual device. So a device physicist can do that by changing the threshold voltage of the devices. So there would be these three different operating regions, and we'll come back to BJTs later. But eventually, what you understand from here is that the BJT is a current-controlled current source, and alpha is going to be the ratio of the currents at the output to input. So if your output current is IC and your input current is IE, alpha, which is the ratio of IC over IE, is going to be called one of these current gain factors. Right? And in reality, alpha is in between, is almost very close to 1. The input current and output current for a BJT, or I will not say input current to output current. So basically the ratio of IC over IE, that's very close to 1 for a BJT. You can also find out alpha in AC mode. So that is going to be del IC over del IE. You can also do it as an average AC mode. So you take delta IC over delta IE. But if you take a derivative, it will become del IC over del IE, just like we saw in the diode classes. Yes.
For PNP, where current flows out of the base as well as the ideal alpha also 1.
Yes, in both cases, the ideal alpha is going to be very close to 1. We are going to see when you come back to BJTs once again, is that the current flow through the base is going to be very small. So the maximum amount of current is going to be passing between emitter and collector, because emitter is the source, collector is the sink. The base region is just a controller through which a small amount of current will. So for both PNP as well as NPN BJTs, the base current is always going to be very small. That means the ratio of IE and IE is almost going to be 1. All right. So IC over IE, that's going to be alpha. There is another concept which is called beta, or which is defined as, let's see if I have it. The beta is defined as IC over IB. The collector current over base current, that is defined as beta. So alpha and beta, these two things we are going to use when we discuss BJTs later on, after we complete our MOSFET discussions and come back to it. But today, I just wanted to give you a hint of what BJT is. It's basically a current-controlled current source, and you can control the output current with whatever input current you apply. I am going to actually show the derivations of each one of those curves as well as the equations later on in the course. But first, I want to do the same thing for MOSFETs because that is easier to understand, because the input is a voltage in that case. And then we'll come back to BJTs once again. All right, so let's end here today, and we'll continue with MOSFETs in Friday's lecture.